The big idea about related rates in this section is to be able to find how much a quantity is changed respect to how fast another quantity is. And the point is that maybe, for example, we want to know how much the volume changes, and volume is something that it's more difficult to measure than compared to, let's say, radius or height, which is just one dimension. So this is the idea behind it, and it's used in biology and chemistry and engineering in general. So we're going to start finding out some kind of equation that relates all the things that we want to study, like volume, like radius, like height, like distance from the bottom of a ladder, or the height of a tree, or things like that. And then we're going to use chain rule to differentiate both sides of the equation respect to time, and keeping in mind that all those measurements may or may not change respect to time. And remember that if they don't, then the derivative will be 0. This is when studying basic geometry pays off, and finding the area, the surface area and volume of different shapes. It says air is being pumped into a spherical balloon so that the volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So there are several things that I want you to be aware. They are not telling you that it's a sphere, but it says a spherical balloon. So that makes me think of a sphere. Now it says the volume increases. So rather than thinking of surface area equation, I'm going to think of the equation of the volume for a sphere. It says increases at a rate of 100 cubic centimeters. So the volume, remember the volume would be in cubic centimeters, and therefore the change of volume respect to time would be on cubic centimeters per second. That means whenever I'm finding time, or whenever I'm finding some kind of measurement about the balloon, is going to be in centimeters, and the time will be in seconds. It says how fast is the radius of the balloon increasing when the diameter is 50 centimeters. So the diameter is 50 centimeters. I know my formula for volume is going to take into consideration the radius. So let's just find the radius right away. The diameter is double of the radius, so the radius will be 25 centimeters. So whatever it is that I find in the equation is going to have the units either centimeters or it's going to have seconds. So the book suggests the d over dt notation. What I would suggest is the prime notation, because the equation may look more overwhelming just by including the Leibniz notation, or d over dt notation. So the prime notation is going to have my equation to be written in smaller. And the other thing to remember here is that what are the dimensions that depend on time. If the volume changes over time, then v prime will not be 0, and if the radius changes over time, then the derivative of radius respect of time would not be 0, or dr over dt will not be 0, it would be something. So those are the things that you have to keep in mind. So the other thing that you have to keep in mind is try to picture the situation. So you're here, this is your nose, and you're blowing a balloon, and at the beginning it's not so much, this is your eye. And then as time passes by, then the balloon is bigger, and then eye, and then it becomes way bigger. So the volume increases, therefore the radius increases. So that's an observation that is simple, but it's going to help us on our calculations, because remember that whenever we talk about derivatives or rates of change or instant velocity, all those numbers, which are the same numbers, they have sign. So if the volume increases, that means V prime will be greater than 0. And if the radius increases, that means the derivative of radius respect to time, or r prime. You can keep writing using the notation that the book is suggesting. That's fine with me. The derivative of radius respect to time is bigger than 0 because both of them are increasing. There will be times where whenever you study a problem, you have to pay attention to whether it increases or decreases. That depends on the sign. So it says, given information, change of volume respect to time. Notice how this is positive. They don't say that, but acknowledge that it's a positive quantity. And this is what they are asking. How fast is the radius changing? So what we're asked, V prime is 100. What we're asked is R prime. I don't know how much that is. When the radius is 25. Now, remember that the radius is changing as the seconds go by. So when the radius is 25 centimeters, that's only one moment in time. It doesn't mean that the radius is always 25, because if the radius is always 25, then the volume is always the same. And then it wouldn't make sense to have change of volume respect of time. So please refrain from replacing 25 at the very beginning of the equation, because that's not the point. So you have the equation that relates volume and radius. So as I said before, unless they ask you what's the initial volume, or what's the volume when the radius is 25, then it makes sense to replace the 25 here. But otherwise, this is the equation that you start with and immediately take the derivative. Do not replace the 25. Do not replace any given information until you take the derivative. So take the derivative first. Please take the derivative first. Take the derivative first. I'm not gonna get tired of saying it. Take the derivative first. All right. So remember that we're doing chain rule. So I'm just going to do the same thing because I can't speak without doing. Derivative of V is V prime, and the derivative of radius respect to time will be the derivative of radius, which is 4/3 pi times r cube is 3r squared, times the derivative of radius respect to time, which is r prime. So canceling out the 3's, I have change in volume is 4 pi radius squared times change in radius. Okay, change in volume equals this much times the change in radius. So what I don't have right now on this problem, you are free to solve in here for r prime. R prime will be V prime over 4 pi radius squared, or at this point you can replace now the given information. That would be fine too. Either way is fine. So change in volume is positive 100 over 4 pi, and the radius squared. The radius, we found that it was 25 only, so 25 squared. So exactly that's how fast the radius is changing, and the units will be centimeters per second because the radius is in centimeters, and r prime will be centimeters per second. So exactly r prime is this much, or dr over dt, and the units will be centimeters per second, or approximately this many decimals. How many decimals you should include? Let's keep it at 4 decimals because you may have to use this information for something else. How would the problem change if instead of inflating a balloon, a spherical balloon, you happen to be done with inflating it, and then it escapes your mouth, and then that's what happens, like it starts deflating on its own until it's completely nice and flat. How would the problem change? Well, in that case, the change in volume would be a negative number. So let's have the same speed, but because it's deflating, it would be, the velocity would be a negative 100 cube centimeters per second. So then they want to ask us how much is the radius changing for when the radius is 25 centimeters. So the equation applies. The equation for volume does not change. And then the derivative of this will not change either. We'll just have to replace v prime with negative 100. And that will give me an r prime that is negative, which is perfectly logical because the radius will be decreasing if the volume is decreasing.